A couple of things about some predictions. So remember, in science, a theory makes a prediction, and we go and test those predictions. And once we can verify them, that hypothesis or that proposal becomes a theory that's backed by the scientific evidence. And so, looking at it in terms this way, your book has a list of predictions that from evolution. So, if evolution theory and descent with modification is true, then these following items should be true. The oldest fossil-bearing rocks should have remains of organisms very different from those existing today. And sure enough, the oldest fossil-bearing rocks are just all single-celled microbes. More recent rocks should have fossils more similar to today's organisms. If we look at just the geologic column, we break the Phanerozoic eon into the Paleozoic era, Mesozoic era, Cenozoic era. The Paleozoic era, we got these ancient organisms. Some of them look somewhat similar to modern phyla, but distinct, very different. Sometimes we don't even have representatives today that were living in the Paleozoic, so ancient. And then Mesozoic is middle, and we do have some reptiles, but we don't have anything that looks like dinosaurs, right? Because the dinosaurs are mostly living in, well, my dinosaurs were living during this Mesozoic period. And then during the Cenozoic era, we see mammals. The mammals in the earlier parts of the Mesozoic were huge, and I'm thinking of the Indricotheres. They were large giraffe-like, in fact, the largest terrestrial mammals that ever lived. They're a little bit different than today, but we can relate to them more closely to modern organisms. Also, there should be fossils showing characteristics connecting orders, classes, and families, and that's that nesting idea of species through time. We should see closely related species should be similar not in details of their anatomy, but also in their genetics or biochemistry, the embryonic development. We should also see a classification of organisms should show how a nested pattern of similarities, and we see that. We would expect cave-dwelling plants and animals to most closely resemble those that are immediately outside that cave rather than other caves, because we're showing that change through time in that geographic extent. We should expect land-dwelling organisms on oceanic islands to more closely resemble organisms from nearby continents rather than from other continents far away. And then finally, we would expect mammals to appear in the fossil record long after the appearance of first fish. We would expect the first reptiles to appear before the first mammals. We would expect the fossil record of related organisms such as horses and rhinoceros. We should find that they were quite similar in their ancestor, but then when they diverged, they became increasingly different over time. And that's what we see in the fossil record. Now we're going to look at classification of organisms. We normally use the kingdom, phylum, class system, and we'll do it for this class, although there's a new way of looking at classification in terms of evolutionary history, and we'll look at that a little bit as well. Carlos Linnaeus in the 1700s proposed this classification system in which organisms are given a two-part genus and species name. For example, we are Homo sapiens. The coyote here is Canis latrans. The wolf would be Canis lupus. The dog is Canis familiaris. Now, they're all kind of this nested pattern where we go from a more broad classification, this kingdom, in this case, multi-cells with a nucleus, sexual reproduction, internal digestion for Animalia. And then the phylum is an important one I want you to know about. Phylum is based on body type or body symmetry. For example, like the mollusks. The mollusks are the clams, the snails, the squids. They have a head-foot body plan, right? So the body plan is a head-foot. Think of an octopus. It's literally its tentacles, its feet are attached to its head, and all its organs are back behind its head in a sac behind the head. For chordates, our body plan, we share this with fish, amphibians, other mammals. Our body plan is that of a backbone, right? And then the subphylum vertebrata is where we have a segmented vertebral column. And that vertebral column, that bone, protects our nerve cord in the chordata here, right? So we need that protection. If we damage our nerve cord, we become paralyzed. Kind of just thinking back a little bit in terms of this biggest picture, right? So even above the kingdom level, we're going to look at these domains of life. And there's three basic domains of life. There's archaea, bacteria, and archaea bacteria differ a little bit in their genetics. And then there's eukarya. And later on, when we start talking about organisms, you'll see that both archaea and bacteria have a type of cell called a prokaryote cell. It's a smaller cell. It doesn't really have a central nucleus. It has DNA, but no central nucleus, and it's about maybe a tenth the size of a eukaryotic cell. So eukaryotic cells are cells that we have, and they do have a true nucleus, right? And so a small segment of the eukarya are animals, and so this would be the clade for Animalia here. Let's take another look here at homologies and analogies. So remember, homologous characters in different organisms that are similar because they were inherited from a common ancestor that also had that character. Four limbs of a tetrapod. Remember, tetra means four legs. Birds, bats, mice, crocodiles all have four limbs. Sharks and bony fish do not. The ancestors of tetrapods evolved four limbs, and its descendants have inherited that feature. The presence of four limbs is a homology. Again, looking at homologies and analogies here, bat wings consist of flaps of skin stretched between the bones of finger arms. So the fingers of a bat are homologous to the fingers of mammals. However, the bat wing and the bird wing, they're similar, but these are more analogous features. Bat and bird wings are analogous. They have separate evolutionary origins, but are superficially similar because they have both experienced natural selection that shaped them in order for them to fly. Now, analogies are the result of convergent evolution. So note that for birds, it's feathers that drop down from the wing bone rather than flaps of skin. So there's a difference there. So when we look at the cladogram, there's four limbs, but then four limbs evolved into wings. But birds and crocodiles are more closely related than birds and bats. So we separate them that way. So just to summarize it up, evolutionary theory is well supported. Evidence comes from multiple independent sources such as fossils, comparative anatomy, biogeography, molecular biology, genetics, embryology, and biochemistry. Scientists overwhelmingly support the core theory. They disagree on specific issues like phyletic gradualism and punctuated equilibrium, and that's really the rates of evolution. Maybe some fossils are more significant than others, and the relationships between. So there's still quite a bit of study going into this, but the overall theme is well supported by scientific evidence. That's it for now.